Hey, my name is Nicholas, and this is my video presentation of Lab 4 on circuits. Introduction. The purpose of this lab is to determine the activity of the circuits with resistors, series and parallel, using the simulation website, analyze the behavior of ohmic resistors and capacitors, measure the experimental values using multimeters, and then finally compare the differences between the experimental and calculated results. A little preview of the results: the two resistor circuits, current equals 0.02 amps. Both the experimental and calculated values both matched in the current and potential differences. More time for the capacitor to charge/discharge when a greater resistance is present. And the RC circuit equals 6 seconds. Fundamental physics concepts that we need to know during this lab. We need to know Ohm's law, capacitance, how much charge can be stored in a capacitor for each unit of potential difference. The node rule: the current entering a junction will equal the sum of the currents from each junction. Loop rule: the difference in potential for a round trip path is 0, and then series and parallel circuits. The lab procedure: the setup consists of two 1.5 volt batteries, two ampemeters, one 47 ohm resistor, one 100 ohm resistor, and then the calculated current of I1 and I2 both equal 0.2 amps. And the system in this lab is the ampemeter or voltmeter, and then the surroundings is the current. The starting circuit: our calculation in the previous slide was correct. The experimental value that we got on the right is 0.2 amps, which matches our calculated result. And if one of the ampemeters is backwards, the value will be negative, which is negative 0.02 amps, replacing one of the ampemeters with a voltmeter, making it an open circuit. We got the experimental values to be 3, and then the predicted value was also 3 volts. And here we can see that the predicted values and experimental values both match. And then potential differences: when closing the circuit with a wire, there's a voltage drop. And here we saw that delta V from A to B equals 3 volts, from C to D equals negative 0.96 volts, E to F equals negative 2.04 volts. And then using the loop rule to confirm this, they all summed up to equal 0. And here on the right, we can see the graph where the voltage drops happened at E. In this circuit, we will add an ampemeter so that it is parallel with a 100 ohm resistor. And then the experimental value that we got was 0.06, which is an increase from the 0.02 volts. And then the current will flow through the ampemeter instead of the 100 ohm resistor because the ampemeter has a lower resistance. And then the predicted value was also 0.06, which is matching the experimental and predicted value. And then these are the new resistor calculations that we got. Here we will construct an RC circuit. This resistor capacitor circuit contains a 10 ohm resistor or a 20 ohm resistor, and then 200 MF calculator and a 9V battery. The 10 ohm resistor charging time was about 15.3 and discharging time was about 15.1. Here we can see that they're fairly similar. And then when doubling the resistor had also increased the charging and discharging time. And this is our time-dependent voltage. We're making another RC circuit with a 9V battery, but this time we'll have a 30 ohm resistor. And then here's the calculation for the slope. And then our experimental value was roughly around 6 seconds approximately. And then our predicted value also matched that 6 seconds. And then discussions: what if we were doing this lab in real life and used an actual ampemeter instead of an ideal simulated ampemeter? What's the difference between a real ampemeter, and how would it affect the circuits you hooked it up? A real ampemeter has zero resistance, even if the resistance is small. This would decrease the circuit and or decrease the current in the circuit slightly. The current readings would be affected. What if you were doing this lab in real life and used a real life battery to charge a real capacitor with no resistance in the current? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? My model would predict that the capacitor would change because there's no resistor in the circuit, but the real life batteries have an internal resistance so that the capacitor would not change instantly. And this concludes my video presentation for Lab 4.